simple random variable takes 6 values, all of them equally probable. Indicator of an event, which indicates if some elementary event of S belongs or not to an event, indicates that by taking the value 1 or 0. And I want to revisit this a little bit because we're going to use it in what we're going to do next. So in this example, we simply wanted to check that this condition is satisfied for all the values X in R. And for that, because of, this is a piecewise defined function, right? For some elements, it takes some values, for others, another. We had to look at different cases where this little x comes from. X should be any real number. So is it less than 0? Is it between 0 and 1? Why were these the cutoff points? Because of the values that the random variable takes, right? 0 and 1. So later when we put it in a PDF, we always list them in increasing order. That's the order that they would go. So 0, 1. So the set of all real numbers is then divided into the subsets from -infinity to 0, between 0 and 1, and then from 1 to infinity. Okay, so x less than 0. This was the empty set, this event, or the impossible event. Of course, that always does belong to any sigma field. For x between 0 and 1, this set was the complementary event of A, which again belongs to the sigma field because A did that, right? And that's one of the properties of a sigma field. Like I said, contains all the usual operations with set. And finally, for x greater than or equal to 1, we got the entire sample space. So notice sort of a pattern here. As we started with x, from the lower to the higher value, so starting from -infinity. First, we got the smallest event, the empty event. Then it was that union with the complementary of A. Of course, that's just the complementary of A. We didn't write the union anymore. Then we took that and union with something else, which was with A, until in the end we got the entire sample space, right? So we started with the impossible, the smallest one, and then kept adding, as in a union, for sets, until we got the largest event possible, the entire sample space. Okay, discrete random variable. This is the only type that we've discussed so far. If it only takes a finite set of values, then it's called a simple discrete random variables. And the examples we had so far are simple random variables. And then sort of a general way of writing a discrete random variable is to use any partition. See here, it was the special type of partition formed by an event and its complementary event, A and A bar. We can do that for any partition, right? And we assign a value to the random variable depending on which set of the partition the element belongs to. Remember, being a partition, that means each E can belong to one and only one such set, right, of the partition. Okay, so it belongs to an AI, then it takes the value xi. And we also mentioned the first important function associated with any random variable, that's going to be true for the continuous ones as well. But for now, just for the discrete ones, is the PDF, probability distribution function. You've probably already seen it by now at the lab also in MATLAB. MATLAB uses this shortcut notation also. PDF, probability distribution function, or probability density function would be the same thing. What is this? This is simply a way of giving us all the information about a random variable. What information is that? The values that it takes, right? Being discrete, that means we can list them somehow, as in either list all of them, if it's a finite set, or list a rule. Okay, again, because it is countable. So values and corresponding probabilities. Takes these values with these probabilities. Of course, to get a better idea, the values are all distinct. They're listed in increasing order, so we get an idea here. Which values of the entire real line does this random variable take? So that's the PDF values probabilities. Of course, because we list all the values, the sum of the probabilities in a PDF is always equal to 1, right? Those events, the fact that X takes each of those values, form a partition. That means the sum of their probabilities is the probability of the Shor event, which is 1. So for the two examples we had, rolling a die, this is the PDF, right? Values, probabilities. So like I said, that was the reason for random variables. We have all the information here related to that experiment of rolling a die. The PDF of the indicator, again, one of the simplest PDFs, two values, probabilities P and 1 minus P. Okay, so now we will go further. The second important function associated with any random variable, and I do emphasize any. This is the definition that goes both for the discrete or the continuous case. So for any random variable, we defined a function denoted, that's a classical notation, by capital F. If we want to make, if we have several variables, we want to make sure we emphasize this is the CDF of the variable X, defined from R to R, real function, by the following simple formula. It assigns to any real number X the probability that the random variable, capital X, is less than or equal to that argument X. And now we see the need for that condition in the definition of a random variable. Like I said, we wanted to make sure that this event is always in the sigma field for any real number X, so that this probability is always defined. This function is called the cumulative distribution function, or simply the distribution function, in short, the CDF. În română, funcție de distribuție îi mai spune, dar mai degrabă funcție de repartiție. Okay. So, CDF, in short, cumulative distribution function, or just distribution function. So, we want to refer again to that indicator of an event example, because that will reveal some features, some properties of the CDF that actually most of the CDFs, actually some of them, all the CDFs have. All the CDFs for now of discrete random variables. Some of them will actually carry on to the case of continuous random variables as well. So that's why I reminded you how we took these cases, right? Because now to find the CDF of that indicator random variable, we need to do the same thing. We need to compute this probability here. Just like back then, we only checked the fact that this event was in the sigma field, again, so that its probability was well defined. So recall, for X less than 0, this event was the empty set, or the impossible event. That means its probability is 0. Then for X between 0 and 1, and here we have to be careful where we include equality and where the inequality is strict. Okay, I'm going to comment on that a little more later. For X between 0 and 1, this event was A bar, the complementary event of A. A had a probability of P, so the probability of its complementary event is 1 minus P. Finally, for X greater than or equal to 1, this event was the entire sample space, so the certain event. That means its probability is equal to 1. Now, See, the definition of the CDF is with less than or equal here, right? So that's why we have to be careful here where we allow equality and where we don't. Here it has to be strictly less than 0, because if um, x is equal to 0, then this is no longer the impossible event. Remember, capital X, the random variable, does take those two values, 0 and 1. So yes, it could take the value 0, therefore we don't have the impossible event anymore, and we don't have the 0 probability anymore. So 0 is included here in the second branch of this function. On the other side, the other endpoint at 1, again, we cannot include it here because x also takes the value 1, capital X, the random variable. So by that time, if we include 1 here, both the values that the random variable takes, 0 and 1, would already be here. So equality goes here. This is not going to be a continuous function. That's why it's important to look carefully at those points where something changes, where we get more possibilities, let's say here, so that we can compute that probability. So this is what the graph of the CDF looks like. Okay, so when x is less than 0, it's the constant value 0. For x between 0 and 1, another constant value, which is 1 minus p. Remember, p is a probability, so it's a number between 0 and 1. So is 1 minus p, a number between 0 and 1. So that's where it is. And then for x greater than or equal to 1, so from here on in, the constant value 1. Notice I put those little circles to show at these points where we have discontinuities, these jumps in the graphs, which of the 2 points actually belong to the graph, right? So it's never coming from the left. The value is not the one coming from the left, but coming from the right. Of course, that only matters at 0 and at 1. At all the other points, there's no problem coming from the left, the limit from the left or from the right. So limit from the left at 0 is 0, but from the right it is 1 minus p, and that's the value of the function also. So I put a little circle here. That point does not belong to the graph. Same thing at the value 1. Limit from the left is 1 minus p. Limit from the right is 1. This point doesn't belong to the graph. The value is the one coming from the right, so another circle here. See, this looks sort of like a step function. We have these stairs, right? Staircase. And like I said, these properties are going to be true for all CDFs of a discrete random variable. So let's look at them, those properties. First of all, how did we actually compute that value? So we started with 0, then as x advanced between 0 and 1, we added a probability. That was the probability that x is equal to 0, 1 minus p. And then as we went further to the right, we added another probability, 1 to 1 minus p, which was p, so we got the entire thing to be equal to 1. This is what we do in general, right? So the definition of the CDF is probability that capital X, the values of capital X, are less than or equal to little x. And little x, remember, is any real number. So no matter what type of values the random variable takes, like discrete values in this case, this little x is any real number. This is defined on the entire set R. Okay, so how do we actually translate this event in the discrete case? Well, we're simply looking at the values that the random variable takes. And those values are listed here in the first row, right? So to say that capital X is less than or equal to little x is to say its values, which are xi, are less than or equal to x. right? And then those are simply going to be, like in the previous example, mutually exclusive events. So to get that probability, we'll simply add the corresponding probabilities. Again, which ones, which PIs? The ones corresponding to those values xi that are less than or equal to x. This is important to mention because when we get to continuous random variables, everything that is expressed in terms of sums in the discrete case will become an integral in the continuous case. You do remember integrals were actually first defined as Riemann sums, as a limiting case of a sum. That's exactly what's going to happen here. Starting with this, the definition of the CDF, the fact that the sum of all the PDFs has to be equal to 1, that's going to translate to the integral, and so on. Okay, so the actual computational formula, right? What was earlier there, that's the definition, the general definition. Discrete or continuous random variable, that's what the CDF is defined by. The actual computational formula, when we want to do it in examples, for the discrete case is this one. And then we can go further. Probability that X belongs to any subset of R, right? Basically, this is a subset of R, the interval from -infinity to little x, right? Any subset of R, it's going to be the same thing. We're looking at those values of X, of the random variable that belong to that set, and add the corresponding probabilities. Okay, now, actually here we do give an example later on because the subsets of R aren't very interesting. You can't have that many subsets other than intervals or maybe unions of intervals. When we're going to talk about vectors, things can get more interesting. In plane, in R2, we can have more interesting subsets. Anyway, let's get back to this. We want to see the type of properties that a CDF function has. And again, these are going to be true in any case. By any case, I mean discrete or continuous. We will get back, revisit these when we define continuous random variables, and we'll see that some of them in that case will be simplified. So for any random variable, notice it doesn't say discrete. With CDF F, again, the definition of the CDF is the same for both cases. F has the following properties. So this is, like I said, a case of a subset of R. On the real line, an interval. In the discrete case, we have to be careful, again, what type of interval it is, where is it open, and where is it closed, okay? You've seen in the previous example, it does matter whether a point is included or not. So this is open on the left and closed on the right. This is simply f of b minus f of a. In fact, the reason for the CDF function, why it was introduced, was just exactly that, to help compute probabilities regarding a certain random variable. The very definition is a probability, but then most of the time we can express any probability regarding that random variable in terms of its CDF. So that was the purpose, the goal for that. Okay, so probability that X belongs to the interval AB open at A, closed at B, is the difference of the values of the CDF at the endpoints. F is monotonely increasing. So why monotonely and not strictly? If A is strictly less than B, we have f of A less than or equal to f of B. For it to be strictly increasing, we would have to have the same strict inequality here. That will, however, be true in the continuous case. About the fact that it's got those jump discontinuities like we've seen in the previous example, that happens for every discrete random variable, and the continuity is always coming from the right. So it's right continuous or continuous from the right. I don't know which notation you're familiar with or which one you remember for the limit from the right. This is one such notation, x plus 0, x minus 0, limit from the left. Or we can be more specific and write it down like a limit. So the values do approach x, but from the right. So coming from the right of x, from greater values, they decrease towards x. Okay, so function is right continuous. The end behavior, end as in END, the behavior at the ends of the domain. The ends of the domain are minus and plus infinity, right? It's defined everywhere on R. Okay, the limit at minus infinity is 0, and sometimes we write that in short as f of minus infinity, which isn't quite correct mathematically, but we know what we mean by that. So f of minus infinity, 0, f of plus infinity, the limit to the right is 1. And then how do we express other probabilities? Because like I said, that was the reason, the purpose for this function, to compute probabilities with it. The probability that x is strictly less than x, which many times is not the same thing as x being less than or equal. It certainly isn't the same in the discrete case for discrete random variables. So the probability that x is strictly less than x is the limit from the left of the CDF at the value x. Again, I used both notations here. The probability that x is equal to x is the difference between f of x, which is also the limit from the right, minus the limit from the left. So see this right here, that would be the relationship between the PDF and the CDF. That relationship will be much stronger for continuous random variables, but even here we can see a relationship, right? This is the PDF. That's exactly what that little p was, probability that x, the random variable, takes a certain value. So the PDF is the difference between these. Let's see why some of these are true. So some selected proofs, not the ones that are very technical, like about continuity here. We're going to skip that, but the ones that are fairly easy to understand. Like the first one, probability that it belongs to a interval, to an interval. Okay, we want to express this. We want to get to the CDF, right? The CDF at a point means the probability that x, the random variable, is less than or equal to that value. So we're looking at these two events, x less than or equal to a, x less than or equal to b. Now, obviously, if a and b are real numbers where a is less than b, strictly less, then this event, or this inequality, let's say for now, from this inequality, it follows the other one, right? Because we could just continue here. X less than or equal to a, which is strictly less than b. That obviously implies that x is less than or equal to b. So now when we look at these as events, that means this event implies or induces. Remember, we discussed this at the very beginning. As events, we say implies or induces, but as sets, that basically means inclusion, right? This event implies, induces this event, which means the intersection of the two is going to be the smaller one, right? When A is included in B, sets, I mean, A intersected with B is the smaller one, which is A. Then we can express this probability. And again, this is just think about what they mean, or think about sets, events here. X is less than or equal to B, so this part, and x greater than a is the same thing as saying x is not less than or equal to a, right? The complementary event. But then, of course, such an intersection, an event intersected with the complementary of another event, is the same thing as the minus, the set, the difference, the set difference of the two. X less than or equal to B minus X less than or equal to A. Okay, for this type of probability of the difference, we have a formula. It's the probability of the first one minus the probability of the intersection of the two. We just discussed that the intersection is just X less than or equal to A. So now these are both the values of the CDF. So F of B minus F of A. Part B. This is a direct consequence of part A. If A is less than B, then what we just proved before is the fact that this difference is a probability. Any probability is non-negative, greater than or equal to 0. So of course, F of B will be greater than or equal to F of A. I said we would skip. This is too technical with the limits. Let's look at the end behavior. Limit at minus infinity, straight from the definition, right? Probability that X is less than or equal to X, little x. When this approaches infinity, this becomes impossible, right? For X to take values less than or equal to minus infinity, that is the impossible event, probability 0. On the other end point of the interval at plus infinity, when X approaches plus infinity, this becomes the sure event, the certain event. X will always take values less than or equal to infinity, so probability of the certain event, which is equal to 1. Finally, again in E, we're only looking at the second part. This again is a little too technical. So probability that X is equal to a value. Again, we express that in terms of events, right? We want to get to the CDF, so we want to express it with this probability that X is less than or equal to something. Indeed, it is equal to X if it is less than or equal to X, but not strictly less than X, right? Just like we did back here, only I didn't write it in so many details. Okay, that will be the probability of the first one minus the probability of the intersection of the two. The intersection of the two, again, is the second one, the smaller one, because that one implies or induces the first one. And then both these probabilities are expressed with the CDF. One of them is the value of the CDF at X. The other is the limit from the left of the CDF. So once again, these are common properties to, like I said, any CDF of a discrete random variable. At the lab, if you haven't already done it, you will look at several discrete random variables. In this tool, they show exactly these two functions, PDF and CDF. And you see that all of them have this shape, this step function graph, right? They always start at 0, right? And then they have these steps, right, where they're constants on each subinterval determined by the value that they take, right? So these jump discontinuities always occur at the values that the random variable takes, which we can always see like this because it's discrete. In the end, it gets to the constant value 1, which is all the way to infinity. Okay, so it always looks like this. It's never continuous. Okay, it has these discontinuities at the values that the random variable takes, and at each such value, the value of the function of the CDF is the one coming from the right, not from the left. Okay, so now let's look at common discrete distributions. This is an idea that follows the idea of probabilistic models, okay? Distributions that occur, you know, of the same type. We're looking at the same things. We're using the same formulas to compute their probabilities. So we divide them into classes, like classes of experiments, classes of distributions, okay? So any distribution will be determined by some parameters. We'll always say what that parameter means in terms of what type of values it can take, give the general PDF, and then also discuss a little bit when it occurs, interpretation, you know, things like that. The first such distribution, the Bernoulli distribution. Now, some of these notations are mine. They're not necessarily classical notations. For some of them, I use what MATLAB uses. You know, MATLAB has these shortcut names for all these common distributions. Okay, so these are not set in stone. Okay, I just chose to call it Bernoulli to differentiate it from the binomial. That's why it's not simply B. So Bernoulli distribution, the simplest one. So we always define the distribution by giving its general PDF. First of all, the parameters, and then the general PDF. So we say that a random variable has a Bernoulli distribution with parameter P, P being a number in the open interval 0, 1. It will stand for a probability, this parameter, so that's why it has this domain. If its PDF is this simple PDF that we've already seen, like the indicator of an event. So takes two values, 0 and 1, takes one with probability P, the parameter, and then obviously the other one with probability 1 minus P, because remember the sum of the probabilities in any PDF has to be equal to 1. So, like I said, this is the PDF of the indicator random variable, the one that we just saw. As simple as it is to, you know, understand, to define, to work with, it has a very important property. When it comes to modeling, you're going to have at some point a lab where just simply look at how to simulate some of these random variables. Simulate them on the computer to approximate different characteristics that random variables have, especially probabilities. Okay, so PDFs, CDFs, and then other characteristics as well. This random variable models the occurrence or non-occurrence of an event, right? Did it occur? Did it take the value 1? Or did it not occur? If it did occur, that happens with the probability of that event, which is the sole parameter of this distribution. So for instance, we can think of this as modeling the occurrence or non-occurrence of a success. Remember, many of the probabilistic models are defined in terms of that. Number of successes in a number of trials, or the first success or the nth success to happen at a certain time. Okay, so this comes in very handy because it tells us just that. Okay, it shows whether success happened or not with a given probability of success, P. Okay, now throughout this entire course, whenever you will see something like this, especially when we get to the statistics part, this is the MATLAB command for it, okay? So discrete uniform distribution in MATLAB, you need D because there's also a continuous uniform distribution, and that one will be UNIF, okay? We'll talk the differences, the similarities, and the differences between the two. It's the only type of distribution that has both the discrete and the continuous version. And because they're both simple distributions, there we can really see the differences between a discrete and a continuous random variable. So discrete uniform has one parameter M, which can take any natural values, natural numbers, not 0 though, so starting at 1, if it has this PDF. Now see, when we describe the PDF of a discrete random variable, we may either list all the values if they are finite, or we may list a rule. Now these are finite too. I decided to write it like this, but we must always be careful to specify what type of values those are. Yes, we write k, but then where does k lie? Where does k belong? Okay, so never forget about this part here. Most of the times we are going to write a PDF like this, so the shorter version, rather than writing 1, 2, 3, all the way dots to m. Okay, so it takes the values k from 1 to m, and each of them with the same probability. See, 1 over m is a constant, doesn't depend on the value of k. Hence the uniform. The probability is distributed uniformly on the set of values from 1 to m. That's the idea of a uniform distribution, and that's going to be the idea of a continuous uniform distribution as well, only then the probability will be uniformly distributed not on a discrete set like here, but on a continuous set, basically an interval. All right, so values 1, 2, 3 to m, each of them equally probable with probability 1 over m. Now, why 1 over m, right? So, okay, I get it. They wanted to have all of them to have the same probability, therefore uniform distribution. Why this particular value? Why? Because the sum of the probabilities in a PDF has to be equal to 1, right? So these would be m equal values, right? M equal values added up would be m times that constant. That has to be equal to 1. Therefore, that constant has to be 1 over m. So this is not by accident. Okay? It has to be this constant. Okay, easiest way to picture it, that example that we talked about, rolling a die, the experiment of rolling a die, let x denote or let x be the number that shows on the die. That's a discrete uniform distribution with parameter 6. Indeed, takes the values from 1 to 6. They're equally probable, and each has probability 1 over 6. Now, the next few models come directly from the next few distributions come directly from the corresponding model. Okay, so binomial, hypergeometric, geometric, those will all be strongly related to the corresponding model. A random variable x has a binomial distribution, MATLAB name BINO, with parameters n and p. They're the same parameters that the binomial model had. That is, n is number of trials, takes natural values, natural numbers, p, probability of success, values between 0 and 1. And whenever there's a p, which is probability of success, there's also a q, probability of failure. So 1 minus p. So a random variable has such a distribution if its PDF is given by this. Now, before we actually read this, let's see where it actually comes from. Corresponds to the binomial model. Let's recall the binomial model. In n Bernoulli trials, n the first parameter, what were Bernoulli trials? First of all, independent. Secondly, in each of them, we're looking at having success, failure. Again, that's not a restriction. We simply divide the sample space into success and everything else, which is failure. And thirdly, the probability of success at every trial is the same, that other parameter, p. Right? That was the setup of the binomial model. And then the model gave the probability that k of those trials were successes. Now, we refer to that again, given n Bernoulli trials with probability of success p, let x denote the number of successes. How many successes can there be in n trials? any number from 0 to n, right? And again, we describe the entirety of what can happen. Remember, that was the purpose of random variables. All the possible numbers of successes in n trials. That's any natural number from 0 to n. Those are the values. What's the probability for each value? Well, that's exactly what the binomial model gives, right? Probability of k successes in n trials. So that's the formula from the binomial model, combinations of n taken k at a time, p to the k, q to n minus k. Remember that back then when we discussed the model, we did remark on the fact that if we add all these probabilities for all the possible values of successes, all the possible values of k, we end up with 1. Okay, so we know that this is correctly defined. This can be a PDF, right? The sum of all probabilities, the numbers on the second row of a PDF has to be equal to 1. Another thing that we want to notice here, see, I said you will see here in a rectangle the MATLAB name for each distribution, but I didn't put any name here for the Bernoulli one, although I emphasized how important it is in modeling occurrence or non-occurrence of a success. Well, that's because the Bernoulli distribution is actually a special case of the binomial distribution, right? So let's see, Bernoulli says, does something occur or not with a given probability P? Well, that's the same thing as saying in one trial, do we have success or not? Do we have success or failure, right? So that would be the binomial distribution with parameters 1 and p. In one trial, success or failure. Okay, that's one relationship between the two distributions. Another one also important, especially when it comes to simulating these computer simulations of these variables, will be revealed a little bit later. Okay, so Bernoulli distribution, special case of a binomial, right? So it can still be, you find it in MATLAB with the same name, bino, only the first parameter is equal to 1. Okay, this looks like a good place to take a break. So let's do that. And I will see you back in 10 minutes, okay?
Okay.
And we are back. Right? Okay.
Yes.
Before we continue, there was something I wanted to tell you. You know, starting with seminar 2, we have those bonus problems. Uh, Again, after you do the seminar 2, then you have 2 weeks until the next seminar to turn them in. Turn them in means you write them down, you know, on paper, and then you scan it or photograph it and send them by email to whoever teaches your seminar. Now, 2 things about that. First, please try to make it as clear as possible, you know, to read. Like write in pen or something, not pencil, because it doesn't look very good. I've received a couple of them and it's not very clear, you know, to read them. That's the first thing. Second thing, actually, 3 things. Don't forget to write down your name and your group number. Okay, very important. And thirdly, uh, both me and my colleague who teaches the other seminars will only grade them all at once. So even if you turn them in sooner than the deadline, don't expect an answer right away. Okay. When the deadline is over, you know, about a certain set of bonus problems, then we grade them all at once because that way is the fairest way. Then we have the same, you know, standards and everything, and then you will get back the results. Okay. So don't get anxious if you don't get an answer right away because you're going to get it once everything is over. Okay, so let's continue with common distributions, common discrete distributions. So we saw Bernoulli, the easiest one, discrete uniform, and then some that come from the model with the same name. All of them but one. There is one uh, exception to that rule. You know, it doesn't come from the model, even though there is a model with that name, but it's a very notable and important exception. But for now, we just stick to the ones that come from the corresponding model, like the binomial one. Right, so basically binomial distribution, the number of successes in a binomial model. Then we go to the next one. Remember, the hypergeometric model was the version without replacement of the binomial model. Other than that, we're interested in the same things. Number of, let's say, successes in n trials. But being without replacement, that changes everything, including the parameters. We need more information than just that probability of success, that proportion at the beginning, because it will only be that at the beginning, being with trial to the next. Hypergeometric distribution, MATLAB name Heige, 3 parameters, capital N, N1, and N, all of them natural numbers, has this PDF, and again, comes from the corresponding model. So in a hypergeometric model, let's remember, there were n objects, and one of which were, let's say, successes. They had a certain property, a certain trait. N are selected without replacement, and then we're interested in the probability that k of those n are successes. So k of those n come from those n1 objects at the beginning. Now, again, just like with the binomial, we say let x be the number of successes in a hypergeometric model. And see, sometimes we say x has a certain distribution or x belongs to the family of distributions with a certain name and certain parameters. So you may see this or you may see a tilde, you know, it means the same thing. X belongs to that family of distributions. So again, now the PDF is clear. How many successes in n trials? Again, number, any number from 0 to n. none of them are successes or all of them are successes, natural numbers in between, each with the corresponding probability given by the hypergeometric model. The formula totally different from the binomial one because being a model without replacement makes all the difference. Negative binomial or Pascal distribution, again, comes from the corresponding model. Both names are used for this, negative binomial or Pascal. Maybe when people refer to the model, maybe the name Pascal is used more because he was the one who, first described it. But then when people refer to the distribution, probably more often you will see negative binomial. Okay, but remember they're one and the same. Okay, but for instance, in MATLAB, you will not find the name Pascal. You will only find negative binomial. MATLAB name and bin, 2 parameters again, an n, which is a natural number, and a p, which is probability of success. So values in 0, 1. They don't have the same relevance, though, as in the binomial model. Let's remember the negative binomial, the Pascal model. In infinite sequence of trials, Bernoulli trials, with probability of success p, that's the first parameter, the model gave the probability that before the nth success, there were k failures. That was the model. Now we define the random variable as being that number of failures that occurred before the nth success. So values, now this is the first one where we see an infinite set of values, but it is countable, right? 0, 1 to infinity. Again, theoretically, we could have that many. In practice, we stop. We stop when this happens, when we hit the nth success. But theoretically, there's no finite number that we can set beforehand to say we stop at 100, we stop at 1,000 trials. So k takes values from 0 to infinity, and the probability for each value is the one given by the negative binomial model. Here's the formula, combinations n plus k taken k at n plus k minus 1 taken k at a time, p to the n, q to the k. Again, remember the sum of all these probabilities for all the possible values of k, which makes it an infinite sum in this case. So a series is equal to 1. By the way, that the same thing was true in the hypergeometric model as well. The geometric model was a special case, particular case for the negative binomial, but because it has so many applications on its own, it is treated sort of on its own. So we have a geometric model, we have a geometric distribution. Like I said, special case for the previous one. Let's see, it is treated on its own even in MATLAB. It's got its own name. Special case when we're talking about the first success in a negative binomial model. So the geometric model said in an infinite sequence of Bernoulli trials with probability of success p, the probability that before the first success, n equals 1, there are k failures was given by this number here. Now again, we define the corresponding random variable as that number of failures that occurred before the first success in a geometric model. Again, a discrete random variable with an infinite set of values, countably infinite, starting at 0 to infinity, and the corresponding probability coming from the geometric model. When we add these probabilities, again, it's a series, and actually that's the geometric series, right, where all the terms are in a geometric progression, and hence the name of both the model and the distribution. Again, this is a particular case. It's the negative binomial distribution when n, the first parameter, is equal to 1. And just like with binomial and Bernoulli, we're going to see later on another important relationship between the two. Finally, very important distribution, Poisson distribution. We had a Poisson model, and this is the only one that has nothing to do with the model. They don't share anything except the name. Okay, this does not come from the Poisson model, unlike all the other ones that shared a name with a model. You can see that from the very beginning when you look at the parameter. Let's recall the Poisson model was what? Was sort of like the binomial model, except we allowed for different probabilities in each trial. So instead of just one P, probability of success in all trials, we had P1, P2, up to Pn, different probabilities of success for each trial. Example, the 3 shooters problem that we discussed at the seminar, actually at both seminars, 1 and 2, right? 3 shooters aim at a target. They have different probabilities of hitting it, okay? So those would be 3 trials with different probabilities of success. Find the probability of, I don't know, the target being hit once. That means 1 success in 3 trials. The target being hit twice, 2 successes in 3 trials. That was the Poisson model. The parameters were n, number of trials, and then P1, P2, all the way to Pn. See, there's nothing like that here. We have one parameter, which can take any positive values, real positive values. Okay. Also, when you look at this, this looks nothing like the formulas we saw for the Poisson model. So it has nothing to do with the Poisson model. Let's see, what does it have to do with? Where does it come from? Poisson random variables arise in connection with what are called Poisson processes. That means processes where we observe discrete events. And when we say discrete events, we mean something that we can count, right? 1, 2, 3. Discrete events are being observed in a continuous interval of something that is measured continuously, like time, length, space, and so on, area, volume. I underline time because most of the time that will be an interval of time. Number of discrete events that occur in a given interval of time. Okay, but it's not necessarily only time. Okay, but something that is measured continuously. So we can talk about an interval of that quantity. Then the variable that has a Poisson distribution is that number of occurrences. Occurrences of that discrete event in the fixed interval of time, length, or whatever that is. For example, number of gas emissions taking place at a nuclear plant in a 3-month period. Right? Whenever we say number of something, those are discrete events, something that we count. It's measured in an interval of time. Time is a continuous quantity. Number of earthquakes that happen in a certain area in a year. Again, number of something, earthquakes, that happen in an interval of time, continuous. Number of white or red blood cells in a drop of blood. Now the drop of blood, that would be volume, right? Again, something continuous, but in that interval, a drop, you know, whatever that volume is, we're counting something. And that is number of white or red blood cells. All these would be examples of Poisson random variables. Number of messages that come into, I don't know, an email account or some communication center in an hour. Same idea. Number of errors that occur in some code, you know, again, in some interval of time. So that's a Poisson distribution. Its parameter represents the average number of occurrences of that event, that discrete event that we're studying in that interval of time or whatever it would be, okay? But mostly, like I said, it would be time. So, for instance, we say in California, there's an average number of, I don't know, 5 earthquakes per year, okay? The number of earthquakes that take place in 2020 would be a Poisson distribution with parameter 5, okay? So those are Poisson distributions. Also, you may find it in many books that it's referred to as the law of rare events. Basically, these, what we call discrete events, are also called rare events. Now, the concept of a rare event is actually well defined in statistics, rigorously, mathematically defined. We're not going to go there because it involves a lot more knowledge than we have or that we need. But intuitively, where it comes from, look at the probability. So again, this is a random variable that takes an infinite set of values, right, from 0 to infinity. But as these values get larger, so as k goes to infinity, what happens to this probability? Now, the exponential part, that's a constant, e2 minus lambda, so that's not affected by the limit of k going to infinity. Both lambda to k and k factorial would go to infinity, but the factorial would go much faster to infinity. So that would be the determinant term here, which would make the whole thing go to 0. Now, how do we interpret that? The limit of a probability, or the probability gets smaller and smaller. Well, that simply means that that event becomes less and less probable, right? Small probability, that means it's not very likely for it to happen, to occur. So less probable, not very likely, that makes it more rare, right? So the larger the value of k, the rarer these events become, the less likely. Therefore, the law of rare events. So even though we don't accurately define what rare events are, we'll just agree to use them in connection with a Poisson distribution, number of rare events. Also, another, say, intuitive description, not exactly definition of rare events, would be events that are very unlikely to occur, for two of them to occur at the same time, right? You can't say you have 2 earthquakes at the same time, right? Or actually even 2, one after another in a very short period of time. That would also be known as rare events. Okay, so the law of rare events, the probability, the distribution of that, so number of rare events in a given interval of usually time, right? Values from 0 to infinity, corresponding probability given here. The fact that the sum of these numbers, again, an infinite sum, so a series, is equal to 1 has to do with the fact that this is the Taylor series for the exponential function. So that would be e2 lambda times e2 minus lambda. That would be equal to 1. Okay, so these are mainly the common discrete distributions. We're going to see examples with them at the seminar, at the lab, learn how to recognize them. For most of them, you know, except the Poisson distribution, it will be the same thing as recognizing, identifying the right model, right, probabilistic model. Then we know it's the corresponding distribution. Again, except for Poisson. Poisson distribution, separate from Poisson model. Okay, now we turn our attention to higher dimensions. Right? Everything that we discussed so far for random variables, for discrete random variables, can be very easily generalized to any dimension, to any number of variables. Now, because we're not going to need any more than that, we will just talk about two-dimensional vectors. So they're no longer variables now, they're vectors. Everything will be with dimension 2. So this is going to be a function with two components, x, y, still defined on the sample space of some experiment. Of course, they're random vectors, but now taking values in R2. And you'll see the similarity for everything that we've done, like a discrete random vector is such a function which satisfies what condition? Well, we had this type of condition for the one-dimensional case. Now we have exactly the same thing, but for both components. So the event x less than or equal to x, y less than or equal to y, which means what? Again, we describe it the same way we did for variables. The value of x at e is less than little x, the value of y at e less than or equal to little y. This event, again, should belong to the sigma algebra, the sigma field, and for the same reason, because we want to be able to talk about the probability of this event, we want that to be well defined. Okay, now this has to hold for every pair in R2, right? Everything is now in 2 dimensions. And because we just talk about discrete random vectors, the second condition has to do with that, the type of values that it takes. Again, it should be at most countable, not in R, but now in R2. Again, just like with variables, we're not going to write vectors as functions, so define them like this. Instead, we're going to give the PDF or the joint PDF. Sometimes it's called joint probability distribution to emphasize the fact that it's for a vector, so for both components of that vector, x and y. Joint PDF or simply PDF, actually you can always recognize that it's a vector just by looking at the values, you know, the dimensions. It's a two-dimensional thing. And the PDF will give the same information. Of course, it has to look different because it has to take into account both variables. What information is that? The values of both variables, x values, y values, and the corresponding probabilities. So now we're looking at the intersection of row xi or row I and column j, and we have, instead of just pi, pij. Right? Pij is what? Again, the probability that the vector takes that value. So I wrote it component-wise, or it could have been written as the vector xy taking the value xy, yj, the two-dimensional value, the pair xy, xi, yj, right? So again, values, probabilities, that's what the PDF gives us. Now, some important properties that will be useful later on. We have a random vector, discrete random vector with this joint PDF. We can get the PDFs of the two components very easily from the PDF of the vector. How? By simply adding. So adding all these probabilities either on rows or on columns. Okay. So if we fix one of them, fix I, add all the probabilities on that row, so that means for all j, we're going to get pi, the probability that x equals xi. Same thing if we do it on columns. For a fixed j, add all the probabilities corresponding on that column for all the values of I. We get qj, which is the probability that y equals yj. And when obtained like this, so we obtain the PDF of x, the PDF of y from the vector xy, then these are called marginal PDFs. And you can see right away where the name comes from, right? We get them on these margins. The margins of the table of the PDF. Okay, so the vector, now like I said, from the vector, so from the PIJs, we can always get the PIs and the QJs, the single PDFs of the components. The other way around is not always possible. So simply having the PDF of X, the PDF of Y, we cannot always get the PDF of the vector XY. We will discuss that in a little while. Vectors are mostly important because they allow us to define operations. And operations with discrete random variables are really very easy to grasp, to understand. They're not so much so in the continuous case, but for discrete, they're quite straightforward. So let's say we have two discrete random variables. Their PDFs are given here. We have the joint PDF of the vector. Then we can define usual operations of the two, like the sum. The idea is very simple. We always operate, so whatever operation we're talking about, we always operate on the values, right? We want the sum of X and Y. We're going to add the values of X and the values of Y, right? So this is going to be another discrete random variable with the PDF given by the values are Xi plus Yj. Probability, of course, X has to be equal to Xi, Y has to be equal to Yj, so the probability will be Pij. Since both I and j here, the sets of indices are at most countable, this Cartesian product is at most countable as well, so the result is still a discrete random variable. Now, a few things. We're going to look at some examples in a short time. A few things. First of all, you only operate on the values. You never, ever operate on the probabilities. Think about it. When adding two probabilities, even if they are probabilities, so numbers between 0 and 1, their sum might exceed 1. So you would end up with a probability that's bigger than 1, which cannot happen. Never, ever operate on the probabilities. Just think about what it means. I want to add these two things. Well, I'm looking at the values that it takes and add those values. Another remark, more clear when we look at some examples. Sometimes we might get the same value from different combinations, values of X, values of Y. Of course, remember in the PDF, each value here is from several combinations. We consider them all at once, okay, and put it in the PDF only once. Each value, again, increasing order, each value, distinct value with the corresponding probability. And then it works the same way for other operations. Product, we want product of X and Y. We operate product on the values. Again, so we multiply the values, again, corresponding probability of the vector formed by X and Y. Scalar multiple, this would be an operation only on one variable, multiplied by a scalar, so a constant. Again, we operate on the value alpha xi, and here we only have pi, the probability that x equals xi. Quotient works the same way, operate on the values. Of course, here we have to be careful not to have division by 0, so this only works for a random variable y whose values are non-zero. Other than that, everything's okay. The quotient of the two corresponding probability. And in general, we can talk about a function of random variables. Now, this function should have some properties measurable in some sense. Okay, we're not going to dwell into the details. Regular functions, let's just say, we can define the same thing for random variables. H of x again, everything applies to the values. The random variable h of x will take the values h of xi with the same probability with which x takes the value xi. So that is pi. Important notion when it comes to operations with random variables is independence. Two discrete random variables. So again, when we say two discrete random variables, we give their PDFs. We say that they're independent if the probability of the vector, Pij, right, probability of this can be factored out as the product of the probabilities of each component, Pi times Qj. Now, when we look at this, this should come as no surprise at all. Basically, when we talk about this probability of the vector taking a value, like I said, maybe the most correct way would have been to write as a vector. The vector xy takes the value, the pair xy, xi, yj. Of course, that means component-wise. X takes the value xi, y takes the value yj. This comma here, when we think about it, means what? Think about the way you say it. X takes the value xi and y takes the value yj. And, right? We discussed this at the seminar. That means an intersection. And that's exactly what it is. It's the intersection of these two events. Now remember, we talked about independence of events, and it meant the probability of the intersection of two events is the product of the corresponding probabilities. So that's exactly what we have here as well. Only those events now state that either x or y take a certain value. So this is straightforward from the definition of independence of events. So now if we know that the variables are independent, of course, in the previous formulas, like here, we can write Pi times Qj. Same here. So see, it doesn't matter what type of operations I'm doing to the random variables, so basically to their values. If we have independence here, we have the product of Pi and Qj, but that has nothing to do with the fact that the operation is product or sum or whatever it is. Same here at the quotient. And let's look at some examples, simple examples so that we can do the computations easily. Start with one variable. So the PDF takes the values -1, 0, 1, and the given probabilities. Remember, always the sum of the probabilities is equal to 1. Find the PDF of this new variable y, which is defined as 3x squared minus 1, right? A simple function of the variable x. Again, we operate on the values, never, never, ever on the probabilities. How do we approach it? Well, one thing at a time. First, we look at the values, right? For any PDF, find the PDF of y. First, we're going to find the values that it takes. Then we're going to find the probabilities with which it takes each value. So, for values of x of -1, 0, 1, simply perform that operation, right? 3 times -1 squared minus 1, 3 times 0 squared minus 1, 3 times 1 squared minus 1. We find the values -1. I'm only talking about the distinct values. -1 when x is equal to 0, right? 0 minus 1. And the value 2, both when x takes the values -1 or 1. Why? Because we have the square here, and that annihilates the negative sign, right? It's 3 times 1 minus 1. Okay, so distinct values, only 2 for y, even though we had 3 for x. Like I said, in a PDF, we only list distinct values. So we're not going to write the value 2 twice, even though it can occur from 2 distinct values of x. Okay, then we compute the probability for each value. Simply looking at how did we get this value, right? So for y to be equal to -1, the only way that that can happen is when x is equal to 0, right? So probability that y is -1 is the same as the probability of x being equal to 0. That's the PDF, right? Probability corresponding to the value 0, so that's 1/4. Now, the interest we already saw that that can happen, or that can come from 2 distinct values of x. That's okay. We can compute that as well. Right? So for y to be 2, that means x is -1 or x is +1, or that means union, right? It's the probability of the union of 2 events, which are mutually exclusive, right? They can't happen at the same time. Either x is -1 or it's 1, but it can be both at the same time. So that means the probability of the union is the sum of the probabilities, and both of them are, we find both of them in the PDF. -1, 1/2, 1, 1/4. So 1/2 plus 1/4, 3/4. Thus, the PDF of y is right here, values, probabilities. Okay, so remember, you can always do this type of analysis, and you can always compute this no matter how many combinations there might be, right? So the easy case is something like this. A value of the new variable can only come from one value of the old variable. If that's not the case, like it was here, that's okay, we can still compute it. Let's look at another example. Let x and y be 2 independent random variables. Now, like I said, independence is very important when it comes to operations with random variables. Again, simple random variables were given their PDFs. We want to find the sum, the PDF of the sum. We proceed the same way. First, we look at the values, right? All the possible values of x plus y, which come from all the possible values of x, all the possible values of y, okay? To make sure you don't lose any combination, take one of them, for instance, the values of x, and add one value of y at a time. So -1 plus 1, -1 plus 2. Okay, so that's 0 and 1. Then 0 plus 1, 0 plus 2. That's 1 and 2. And then when we say the possible values of the sum, of course, we only list them once. So the possible combinations are 0, 1, and 2. And again, take each value separately to compute the corresponding probability. Probability that x plus y is 0. When we're doing this by hand sometimes, so at the seminar, I would say let's write down underneath the corresponding combinations, right? What value of x with what value of y would give a sum of whatever's here. Okay, you can still do that. So for x plus y to be 0, the only combination that we get a sum of 0 is from -1 plus 1, right? So that's what it means. Here is where independence is important, okay? If I don't know that they're independent, then I need some other information about the vector, right? Or else I cannot continue, go further, okay? Knowing that they're independent, this is the product, probability that x is -1 times probability that y is 1. We get both of them from the PDFs. 0.02 times 0.6, which is 0.12. Let's move on to the third one because it's just as simple. We get a sum of 2. The only combination to get a sum of 2 is from 0 plus 2, right? The same type of thing. X is 0, y is 2. Because they're independent, this is probability that x is 0 times probability that y is 2. So that's 0.8 times 0.4, 0.32. Probability that the sum is 1. Now we have two different combinations that result in a sum of 1, and that's okay. We can still do this. Either -1 plus 2 or 0 plus 1, right? So those would be the combinations, the pairs listed underneath, right? Again, I said or, that's a union. So first we look at the probability of this union. So we're looking at the fact that these two events together, the event x minus 1, y2, and the event x0, y1, are mutually exclusive. And of course they are, because neither x nor y can take two different values at the same time, right? So because those are mutually exclusive, that means we add their corresponding probabilities. Then for each such probability, just as before, we use the fact that x and y are independent. We need that for this probability of intersection, right? Which means we can split it, we can factorize it into the product of the probabilities. And at this point, we get each probability from the PDF. So 0.2 times, what was it, 2? 0.2 times 0.4 plus 0.8 times 0.6. 48 plus 8 is 56. Now, alternatively, and I specifically left this for last, okay? We could have avoided this part, just like we could have avoided this part here. You can do just some of these computations, and if you're really sure that nothing is wrong, then you can use for the last probability the fact that they have to add up to 1, okay? So like in this case, compute the two easy ones, probability that the sum is 0, probability that the sum is 2, okay? And if you're absolutely sure that nothing is wrong, then you can use those results, because you know in a PDF they have to add up to 1, okay? So compute the third one by simply subtracting the sum of the other ones from 1, okay? But I think it's a good idea to do it both ways. That way you can be even more sure that your result is correct. And same in the first example, right? Compute one of them and then get the other one as 1 minus the other. Finally, a remark, a very important remark when it comes to operations. Remember how we said the Bernoulli variable is a special case of the binomial, and that is binomial with parameter 1, n equals 1 and p. Another important relationship is the fact that, so first of all, the simple one is a special case of the general one. Another way to look at it is the general one can be obtained as the sum of n independent Bernoulli ones. Think about it. Bernoulli variable tells you, let's say, if you have success or failure in one trial. Binomial tells you how many successes you have in n trials. You can just look at each trial one at a time, right, and add the number of successes. Each of them is a Bernoulli variable, so the sum is going to be a binomial variable. Number of successes in one trial, so that can be only 1 or 0. Number of successes in n trials, we add up all those successes. Exactly the same type of relationship between geometric and negative binomial. Again, geometric was the particular case of negative binomial when n equals 1. A number of failures before the first success. Negative binomial, number of failures before the nth success. Again, we can do them one at a time and add them. First, we got the number of failures until the first success. That's a geometric variable. Then the number of failures until the next success, the second one, another geometric variable, and so on until we get to the nth success. This is very important, for instance, when modeling, simulating such variables. You know, if you can simulate the easy one, then you can use this sum to simulate the more general one. It also comes in handy when, in the next chapter, we're going to talk about numerical characteristics of random variables, like mean value, variance, and so on. This is going to make the computation of some of those characteristics very easy by having this relationship. All right, so this is it for, we finished the discrete case, discrete random variables and vectors. Next time, we're going to discuss the continuous ones. The approach is a little different. They're not so easy to see in examples as the discrete ones, but we're going to do analogies with the discrete case. And we're going to follow the same pattern, you know, describe the common ones, then go to vectors and look at some of their properties. Okay, any questions, any comments, anything? No? If no, then we are done for today. Of course, with the lecture. I'm going to have a seminar with some of you today, so I will see you later. Okay, bye. Don't forget to hang up from the meeting.
Bye.
Thank you. Bye.
Bye.